collector curves here, and that's where the collector net voltage is plotted with the collector current on this y-axis. And then your part is then to select a base current from the group of curves for each type of transistor. This image here just shows how the curve is actually generated here. So on a BJT, or an NPN, the base emitter junction is just like a diode, PN junction. And you note that it's also non-linear device. So that means if you overdrive with BJT, you basically create distortion in the device. So this example here is we're trying to get to the point where we can calculate the gain H of V of the circuit. So in the base of the transistor, we apply a base emitter voltage, and then we apply a small AC signal on the base also, and according to the theory, a much larger waveform should appear on the collector of the transistor with a simple model like this. The quiescent point, we develop a base emitter voltage, and that develops the I sub C, and we'll call that our Q point. So in this curve here, we understand that there's hundreds of different Q points on the collector curve, and then your part is selecting the appropriate Q point for the design that you're doing. So quiescent or Q point is lack of input signal. And if there are capacitors in the circuit, you definitely don't want to have the AC input because capacitors charge and discharge. You can change the voltage in that circuit. So this basically is combining these two curves. This is the PN junction on the NPN transistor. And kind of a normal design would probably select a Q point somewhere in the middle of these collector curves. And then I sub B is I sub C over beta. And then we would set up a collector voltage here. And then we'll have a I sub C at this point. And we've gone over problems where we set the collector current, and then we set the collector emitter voltage, and that's called the Q point on the circuit. So this diagram with the line on it, this is kind of an earlier method of finding a Q point for the transistor. This is what's called a load line on the collector curve. So one end of it is connected directly to battery, and the other part is connected to the battery over the collector resistor. So now your Q points, you basically doing is you're limiting your Q points to just a small set of parameters. So you no longer have to arbitrarily pick Q points that are off this line. So you can actually draw your own base currents in here. So there are certain parts you stay away from. This lower curve is too close to cutoff, and this upper curve is too close to being overdriving the amplifier and getting distortion. And then we also stay away from this V right here. This is the VSAT part of the collector curve. So if we take that point and we extend it down to the x-axis, this is actually where our VC and SAT is. So this Q point here is well away from VC and SAT, and it's well away from being cut. So it's kind of an optimum design. The question of where to place the Q point, it doesn't take, as long as we have, in these collector curves, the manufacturer usually will supply some version of these curves to the engineer. And then your part is to go in and use those those curves to pick a cue point where you want to design the circuit. So putting a cue point in the center of these curves is probably the most optimum, and statistically, over temperature and beta and component tolerances, this cue point is probably going to vary. It's not going to stay on that line, it's going to vary off of that line. So you're going to have some percent tolerances on the cue point. So what we'll do is what we're doing here, we're assuming room temperature and beta is constant, and all of the components have 0% tolerance on it. So we don't have to get into the statistics of the circuit. These cue points are all in the active region, even the ones on the low curve and the one that's up here near saturation here. They're still in the active region. And what's a simple expression for active region for BJT? NPN.
What was the question?
Simple expression for active mode for NPN.
Right there.
BJT.
VE is greater than VB is greater than BC.
Yeah,
Is that what you for active it's greater, and for saturation, VB is less than either.
So it would say D sub emitter
I don't know.
is less than D sub base is less than D sub collector. So that's kind of a simple expression for NPN transition. Emitter voltage is less than base voltage, and base voltage is less than the collector voltage. And that's called the active mode. So this graph also shows saturation, and it shows cutoff at this point here, and then all the rest of this plot would be considered the active mode. And this curve here is just demonstrating a group of engineers designing an amplifier, and engineer decided to put the cue point up here, and for choice that calls saturation. Another engineer decided to put the cue point here. Another for choice that's too close to be in the cutoff. And the normal, have a couple of engineers kind of put the cue point in the normal active mode region. Again, it's your decision as an engineer where you want to actually put the cue point in a circuit. Now this small signal parameters, we need to use them to calculate the gain of the amplifier. So definitely want to make sure these equations are on your exam formula sheet. Transconductance G sub M. G sub M is equal I sub C over V sub T, and V sub T is 25 millivolts. If V sub T is not given in the problem, we understand that it's around 25 millivolts. So this is our first small signal parameter, and it's called transconductance. The units of it are milliamps per volt, or we can put it into amps per volt. Now this is getting directly into problem 3 into homework 2, where it gives a complementary amplifier and asks to calculate the gain of the amplifier. So one of the numbers you'll need to calculate the gain is G sub M, which is I sub C over the thermal voltage, 25 millivolts. And this demonstrates 3 versions of I sub C here. I sub C is 0.5 milliamp, and the G sub M calculates 20 milliamp per volt. The engineer decides to increase the gain. I sub C is 1 milliamp. G sub M is now 40 milliamp per volt. And then trying to increase the gain again, and I sub C goes to 2 milliamp. Then G sub M is now 80 milliamp per volt. So the larger I sub C, the larger G sub M. However, the larger I sub C, the more the transistor starts to move toward saturation here. So make sure we're aware of this formula to calculate G sub M. The R sub pi is the small signal input resistance. So R sub pi, we have an equation for that here. It's beta over G sub M. So R sub pi, if something says find R in, R sub pi will be a function of the R in. So we have G sub M, we have R in. So here, another example, beta is 100. If I sub C is half a milliamp, R pi is 5K. And if I sub C is a milliamp, R pi is 2.5K. And I sub C goes to 2 milliamp, R pi goes to 1.25K. So the trend is the larger I sub C, the smaller R sub pi. So if you're trying to increase the input resistance of an NPN amplifier, you definitely do not want to keep increasing the microcurrent. If you do, it moves away from a large Rin or an R pi. Another small signal parameter R sub E is R pi over beta plus 1. And this is the small signal resistance in the emitter of the transistor. Now, what is G sub M in terms of R sub pi, in terms of R sub E? So this formula, you should extract G sub M from this formula based upon what was given for G sub M. The G sub M is I sub C over the thermal voltage and then R sub pi is beta over G sub M. So R sub pi is beta over G sub M. If R sub pi is beta over G sub M, what is RE in terms of G sub M? Assume beta is 100, yes. R pi is beta over G sub M.
Beta squared plus beta over GM.
Let's say beta is 100.
You plug in R sub pi, and then you solve for GM.
All right.
Whatever, is it whatever GM?
If beta over,
That's close to 1.
if beta is 100, then beta over beta plus 1 is approximately 1. So R sub pi is approximately. G sub M is 1 over R pi. So we get G sub M from this equation also. So again, if we iterate the collector current at a half a milliamp, RE is around 49.5 ohms. If we increase the collector to 1 milliamp, RE goes to 25 ohms. And if we increase it even more to 2 milliamp, RE goes to 12.5 ohms. So the larger I sub C, the smaller the emitter resistance. So we have G sub M, R pi, and then small R sub E. The gain of this circuit, we can calculate, and you use the lower part here. You notice there's no load on the collector, and there's no resistance on the base. So the gain of the circuit is minus G sub M times R sub C. Now this equation changes if there's a source resistance or there's a load connected to it. So if we put a capacitor here and we connect a load resistor out here, then we have to compensate for the load resistor because it'll be in parallel with RCC. But without a load resistor or a source resistor, the gain is minus GMRC. So here again, if we iterate the gain as a low current half a milliamp, the gain is minus 60 volts per volt. And we note the units here, if we increase I sub C to a milliamp, we double the current, our gain goes to minus 120. Why do we have this inverted sign here? What does it negative mean? And why is it important to note that?
It's 180 degrees out of phase.
It's out of phase with the input. So on the oscilloscope, the collective waveform would be 180 degrees out of phase with the waveform on the base. But that was channel 1. And if we increase the collector current to 2 milliamp, our gain goes up to minus 240. So we get a very large increase. So the larger I sub C, the larger G sub M, and the larger the small signal gain. We also note the larger we make the collector resistor, and the voltage gain increases also. So we have a couple of ways of increasing the gain: the collector resistor, or we can use the current. So the comment here, basically, these basically mean the same thing as for P and P. Now the circuit here is not practical, but we want to avoid bringing in another battery to bias the base, to create these the base emitter. So the note here is just saying that this Q point, we need to find another way to actually bias the base rather than use that extra battery. So as long as the transistor is in the active mode and the base emitter voltage is small, the transistor should not cause distortion. So putting these small signal models, numbers into a model, we go into modeling, and we're very familiar with models. Many commercial systems develop models before actually investing in building. And architecture, if you wanted to build some new buildings, the architects can first develop models of the building. In aircrafts, whenever introducing a new aircraft, they develop models of the aircraft and they test the models of the aircraft. So transistors can be used the same way. We basically developed what's called a small signal model. This is the simplest. This is a hybrid pi, probably level 1 model for NPN transistor. So we have an R pi term, we have a G sub M times base emitter voltage. Here's the emitter current going in here, the base current is here, and the collector current. And we note the KCL is valid for this symbol here. And our collector current is G sub M, B sub VE, this generator. The base current is B sub base emitter over R sub pi. So this is an AC base emitter. This is not the DC base emitter voltage. So the AC on the base emitter increases the base current basically increasing. So that's just transfer to those equations. Now this model here is something about is superposition. We have an early voltage. You should recall that we mentioned early voltage earlier, and the engineer J.M. Early found that if you take the collector curve and we draw a line from them in negative infinity direction, those curves all converge at a point. And this point where they converge is called the early voltage after the engineers basically came across this concept. So we have an early voltage, and this gives us another small signal parameter called R sub O. So R sub O is the early voltage over I sub C. The manufacturers usually will give a number for the early voltage in terms of volts for a transistor. Just be aware, this is another parameter to calculate. So this example define the hybrid pi model for a collector current of 1 milliamp. Early voltage is 100 volts, and then RO is 100 volts over a milliamp is 100 K. So with this, we still need to calculate R sub pi and G sub m. So we have at least one of the parameters here in terms of the early voltage. Sometimes the early voltage is given as infinite here. If the early voltage is given as infinite, it just means we do not have to include this extra resistor in the hybrid pi model. And that's basically the material we cover for a small signal. The rest of this is there's a combinator amplifier NPN is given here. It appears that all the resistors have been designed. There's a load of 12 K, and then there's a description of the here. Now, if this in the original form of this problem, these numbers probably weren't on here's the author has come in and actually just wrote the numbers next to the parts of here, so that may, when you analyze it, you keep track of it. So it says capacitors have infinite capacitance. That means that this capacitor is an open circuit for DC, and then this capacitor is a short circuit for AC. So the question says, neglected base current I sub B, find values for the base voltage V sub B, V sub E, and I sub E. So what is the base voltage here? The battery is 9 volts. And we know here we wanted to replace the base emitter battery with 2 resistors to bias off of the 9-volt battery. So what's the base voltage here? Again, it's a voltage divider. The battery is 9 volts with 230 K resistors in parallel. So the base voltage is 4.5 volts. Half of that. The emitter voltage is the base voltage minus 0.7, which is 3.8. The emitter current I sub E is the emitter voltage over RE, 3.8 over 6, K, 0.63 milliamp. I sub C, we assume alpha is 1. The problem said neglect base current, so we can assume alpha is 1. And then the collector voltage, the battery minus IC, R sub C, is 7.11 volts. And now we check the active mode of V sub. The emitter voltage 3.8 is less than the base voltage of 4.5, and the base voltage is less than the collector voltage of 7.1. So that brings it into the active mode. The next part of this says to draw this amplifier small signal diagram. So the question like this is on the exam, we'll need to recall this diagram from memory. We're not allowed to draw diagrams on our formula sheet. So here's the bottom here, this is the small signal diagram here, and we need to calculate 4 small signal parameters in order to complete this, draw this, and then find it. So here's R sub E, there's D sub T over I sub C, there's 25 millivolts over 0.63 milliamp, 39.7 ohm, R pi is beta plus 1 over E. Okay. G sub M is probably 1 over RE, 25.2 milliamps per volt. And then RO is the early voltage over I sub C, 80 volts over 0.63 milliamp, 127 KO. So write the small signal parameters near the components on the model. And that's where the author has completed that here. There's a source resistance of 1K here. And you notice the way it's drawn, there's a 1K one source. There's a load resistor of 12.5K. So for AC, this capacitor is a short circuit. So in the model, we just draw the 12.5K in parallel with the collector resistor. Rn, the resistance looking into the base, is RV in parallel on pi, 2.16K. And then calculate the gain, A sub V at the bottom. Now, there's a voltage divider on the input between Rn and R pi of the transistor. So we need to account for that here. And here's our inversion. So the voltage divider is Rn over Rn plus R signal here. So R signal is given as 1K. And the math, that's around 0.76. G sub M, 25.2 milliamp per volt. And then we have 3 resistors in parallel. RO, RC, and RL in parallel with each other. So they give a gain of around minus 45.4. And there are other versions of this type of analysis, but this is probably the most complete analysis, where you have to first do a DC analysis of the circuit and then calculate the small signal parameters, calculate REM, calculate the gain, HV, and then draw the small signal diagram for your circuit. The circuit that we just went over, that's a common emitter amplifier. So, assuming that the circuit is given, this means there's not really a design question. We have the data sheet parameters of BJT, we have the load and the source, and then we have the incoming small signal that we want to amplify. First step, we just went through this with the problem we did. Analyze the DC condition, find the Q point of the amplifier. And that's what we just solved one that was doing problem for. Is second step, compute the small signal parameters. Step 3 is draw the small signal diagram. Step 4, solve the small signal circuit, compute the small signal gain, and compute the small signal input resistance. It says compute small signal output resistance, however, we're basically just going to stay with calculating the small signal input resistance. And then step 5, find out if whatever the input to this amplifier is it too large that it will cause crippling amplifier. If there's clipping, it means we have to probably go back and lower the gain of the amplifier. So here's an example from the emitter into the end. The amplifier appears to be designed, so what is the voltage on the base here?
One half times 12.
Now,
6.
many times R1 and R2 are not the same value, so it's kind of convenient. They're both 20K. So V sub B would be 1/2 would be 6 volts. And what's the emitter voltage?
0.7. I'm sorry.
5.3.
So we have 6 on the base, and that 6 minus 0.7, 5.3 on the emitter. With that, we can calculate the emitter current here, and we'll assume I sub C equals to I sub E. We can assume the collector current is the same as the emitter current, and then we can calculate the collector voltage as the battery minus IC R sub C. And now we can calculate the small signal parameter. The capacitor C3 and C1 are coupling capacitors, and for DC they behave as an open circuit. That's the most we need to go about them. The DC in the circuit is set up like R1, R2, R5, and R4. And these are used to set the Q point of the amplifier. So the equation that we're familiar with here is that the battery voltage, VB, is our R sub B, R1 in parallel with R2, I sub E, and make sure we have this equation. Otherwise, we have to solve the KVL around this emitter loop. And collector voltage, the battery is using a 1/3 loop. So the battery is I sub C RC plus IE RC plus VCE. So the battery is 9 volts. These are all in 3 volts, and they would sum up to 9 volts. So these are our basic formula sheet equation for this type of amplifier. A question probably would ask, find the situation for I sub C and the collector emitter operating in the Q point mode. So this note here, assuming the circuit has constant gain at all loads and sources. However, it really doesn't. But we're just going to monitor just a Q point, and we're going to have a fixed load and a fixed source resistance. And whether this is AC or it could be a pulse, the circuit will basically amplify. And if we keep the input signal low enough, then we won't have clipping or distortion. The AC signal is on the input. The capacitors here, these 1 mF, 1 million farad, that's definitely way too large for a real capacitor. The capacitors are chosen in a design process, and we're not really going to cover the design of the capacitors in the circuit. So if a schematic is given, just assume series capacitors are open circuit for DC, and then this capacitor emitter, this is an AC short for AC frequency. The coupling capacitors, if we kind of just briefly, how do we actually decide on these C3 and C1? We check out the frequency here, say at 100 hertz. The capacitor reactance, we're all familiar with 1 over J omega C, and that's minus J 1.59 ohms. If we go to, that's like a short circuit for AC. If we go to 10 hertz, a lower frequency, the capacitor impedance is 15.9 ohms, which is still small. However, it's basically showing us that if we want to pass very low frequencies, say like 1 hertz or even lower, we really have to get very large series capacitors in the circuit. usually around 100 microfarads are probably sufficient capacity. The bypass capacitor here, this is a short circuit for AC. So when AC appears on the emitter here, basically it bypasses R4 and finds a path directly to ground. So you'll find that this R4 is very important in calculating the gain of this amplifier. So our example is base emitter is 0.7. If the device is on, the beta is 100. So we calculate D sub dB here, 6 volts. RB is R1 in parallel, R2 is 10K. And then I sub E, we use our known equation, 0.98 milliampere. If we use the formula where we remove this RB over beta plus 1, it's around 1, I sub E is around 1 milliampere. And if you're solving a problem like this, it's usually best to keep this term in the equation because it's actually more accurate. So these are the voltages calculated, in terms calculated so far. V sub D, V sub D, and I sub E. And this assumption here, when you're working with a problem, you want to definitely write that somewhere in your result. You're assuming I sub C is approximately I sub E. And this question alpha is not 1 exactly 0.99. So when you work with a problem like this, remember to write down any assumption that you're making in your work here. The collector voltage, V sub C, we just use the voltage drop across the collector resistor. Battery minus IC, RC, 9.5 volts. So if we have 9.5 on the collector and 6 volts on the base, that's active mode for the collector base. The collector emitter voltage, we can subtract the battery minus IC/RC minus IE/RE, and we get approximately 3 times 4 for 12. So 1/3 of that would be approximately 4. So VC is approximately 4.2. That's approximately 1/3 of the battery. So this is a kind of a normal operating point for this amplifier. The small signal parameters, RE, BT over I sub C, 25 ohms. G sub M is 1 over RE, 40 milliamps per volt. And then R pi is beta R sub E. This is actually beta plus 1 RE. It's just leaving out plus 1, 2.5 K. And if an early voltage is given as 100 volts, RO is the early voltage over I sub C, so it's approximately 100 K ohms. So we have the four small signal parameters, so we're ready to draw a small signal diagram. So this is our, from memory now, this is our small signal diagram of the circuit. You notice the emitter is grounded, and that's because of the capacitor across the emitter resistor. RD, the two resistors in parallel, appears here. Here's our pi. Over here, this is RO. Here's the collector resistor, RC. And here's the load resistor, RL. And then on the input, this is our source resistor. So RO, RC is parallel with RL. What's the formula for the parallel resistance of these three? RO in parallel with RC in parallel with RL. What's the formula?
1 over R.
1 over. So
Would it be 1 over R plus 1 over R.
Okay, you make in the inverse form, so -1, and then you take 1 over each resistor and add them together, and take the inverse, and that gives us a parallel resistance. So this is basically a model of this transistor. So we still would probably build a breadboard to check the model, but here we can assume that in replacement of doing a breadboard, as long as we have the model, we can calculate the gain of this amplifier. So now we can calculate A sub B, and then we can calculate R sub n of the transistor. So Rn is Rd in parallel with R pi. And Rd is 10K, R pi is 2.5, so Rn is equal to 2K ohm. The voltage divider on the input is Rs, Rd in parallel with R pi. And Rd has a series R sub S with it. So we need to calculate the voltage divider loss on the input. That's equal to Rn over Rn plus Rs. Rs appears to be 100 ohms, so that's approximately 0.95. So most of the signal passes into the base of the transistor. So it's not equal to 1. The next part is our gain. This is actually A sub B minus GM minus RC parallel RL parallel with RO. And we're assuming a small signal here, so we're going to keep this source over here probably 10 millivolts or less. And then the gain we get here should not have clipping or distortion. So putting the numbers in here, GM minus GM with 40 milliamp per volt, and then we have these 3 resistors in parallel. Notice that that's using an inverse resistor formula. The gain is minus 78.4. If RO is infinite, which is not infinite early voltage, the gain is approximately minus 80. So from the paper analysis, then the assumption the early voltage is not used. There's a very small difference between a real early voltage and not having an early voltage number. Very small difference. The gain in the bottom here, again, is minus 74.5. And the small signal assumption that we're making here, we want to make sure it's valid, just like we did with the op amps. And as long as the input is 10 millivolts or smaller. Now this is actually repeating that example again. So the example here is saying we follow this, find I sub B, neglect I sub B, find B sub B, B sub B, and I sub B. And we've gone over this, and then this part says you draw the small signal diagram, put the values of the small signal components, label on the circuit, calculate Rn, and we notice the author is highlighting the response. On the exam, if the problem is solved and it appears to have multiple results, and there's no deliberate attempt to highlight the desired result, the problem most likely will not be graded. And it's a 25-point problem, and there's at least 3 or 4 results, and there's nothing to highlight which one is the actual desired result. The problem can't be graded. So remember, on the final exam, make sure to highlight result that you are sending to be graded. And here's another problem. This is your homework assignment, is to review these different problems for the common emitter amplifier. Pretty much assured that any one of these problems can and will appear on the final exam. It's a very summary type analysis here which sums up a common emitter amplifier. Now the MOSFET amplifiers are definitely more challenging than the NPN transistors. And part of that is that in MOSFET, there's no equation to, there's no miracle equation on the MOSFET. So there's no I sub C equal beta I sub D. MOSFETs have their own set of equations based on how the transistors actually manufactured. Down in your homework 2, there's a problem 3, and this is basically the same transistor that we've just been covering. It appears different. It has a current mirror in the emitter of the transistor, and then there's no base resistor to drive the transistor. It has a battery B sub CC. What's the meaning of this small arrow here?
Maybe it continues.
Source.
Yeah, so here's a kind of redrawing of the circuit. So the circuit indicates that there's a source resistance of 0 ohm. There's a collector resistor of 9 k ohm, and a capacitor and a load resistor of 22 k ohm. And the emitter is the current source. An ideal current source in the emitter, and at values of 0.3 and 300 circuit, then you're given the emitter current. You don't have to solve for it. You have to solve for the emitter voltage, the base voltage, and the collector voltage. So what is the base voltage on this? You notice here what that little arrow means? It means that this is connected to minus 10 volt DC. So it's a dual polarity amplifier. So the question is asking, find the gain of the amplifier A sub B, and then find Rin of the amplifier. So here, and this is kind of an example result here. Let's say we assume active mode. So if we assume active mode, then this equation here would be true. The emitter voltage is less than the base voltage, and the base voltage is less than the collector current, collector voltage. We can also assume the new equation I sub C is beta I sub B, and then I sub C is alpha I sub B. This is important because this is giving the assumptions being made before starting the problem. So these are the initial assumptions. If you find a contradiction, then we have to go back and revise the assumption. So to start the problem, we need to find the we need to find something about small signal numbers. So we can start with alpha. The problem, we can assume base current is 0, or we can solve for alpha. Here we're solving for alpha. So alpha is beta over beta plus 1. Beta is 120, that's given. So alpha comes out on 0.9917. Of course, you decide on how many decimals you want to carry. And then this equation, I sub C, and because the assumptions were made here, that means that we use this equation. I sub C is alpha I sub E. So that's 0.99 times 0.3 milliampere, and that comes out at 0.29752 milliampere. So we have one of the, we now have the emitter current, and we have the collector current. And then our next step is to find RE. We find R sub E here. RE is thermal voltage 25 millivolts over I sub C. And if you put in the numbers, it's, if you're writing this down, this is 84 ohms. G sub M is 1 over RE, and G sub M is 11.8 milliamps per volt. So we have some of the small signals, so this is right here. And now, input resistance is beta over G sub M. And it turns out in this circuit, the input resistance is just R5 because there's no resistance on the base of the transistor. So that's 120 over 11.9 times 10 to the minus 3. And R5, that means R5 is 10,000 ohms. And the only voltage was given, I believe it's 85, so RO is V sub A over I sub C. So RO is approximately, is a large number, 285.7 k ohm. And now we have all of the small signal. The small signal parameter we need to solve this first part of this problem is G sub M. So A sub B is this equation here. A sub B is minus G sub M times RC parallel with RL and parallel with RO. And I believe this number here is 6,247 ohms, or 6.24 k ohms. If you go through your own math, we'll get a more accurate number. And notice this equation doesn't use milliamp per volt here, so you have to remember this has milliamp per volt. They canceled out the kilo. So the gain of circuit in predicted is about minus 74.3. So with that number, this assumption, you need to go back, you need to make a conclusion about the problem. Is this the correct assumption that was made to begin with? So that's, you have to confront that conclusion. And from that, the base voltage, the base is tied to 0 volt AC. So the emitter voltage is 0 minus 0.7, which is minus 0.7 volts. That's the emitter voltage. The collector voltage is the battery minus IC RC, so that's 10 minus 0.297 milliamp times 9K. The collector voltage is 7.32 volts. And now we check the initial assumption is V sub E less than V sub D less than V sub C. And this is important in the write-up for the conclusion of this part of the problem, because now we're checking the numbers, and it's minus 0.7 less than 0 volts, less than 7.32 volts, and that's yes. And you basically have completed the problem. And now the next part here is to take the circuit and then enter it into T-Spice. So you're basically going to confirm your engineering paper calculation. So here's a version of the circuit. And you'll need to search in probably in the eval library to find this ideal current source. So it has a value of 0.3 milliampere. This is the minus 10 volt battery. And the emitter, you notice the negative side is connected to the emitter. There's a positive 10 volt battery connected to the 9K. The author has put a 0 ohm resistor series with the base. I'm just putting a wire here. And then instead of 1,000,000 farads, he says, you'll decide on your own. The capacitance says just let's use 100 microfarad. The current mirror is a big capacitor. You probably could also put 100 microfarad here. And you need to definitely put a bypass capacitor across this current mirror. If you don't put this capacitor here, the current mirror is going to carry a very high resistance in the circuit. So they both can probably be 100 microfarad, and here's the 22K on load resistance. We put a V out in the circuit, and there's a V in. The input is small signal, 10 millivolts amplitude, and you just decide on your own input frequency. You can use 10 kilohertz, 15 kilohertz, 5 kilohertz, 3 kilohertz. Here it's just using one kilohertz. So this schematic is going to check your paper design compared to your simulation results. So on the simulation profile, I've set up a transient. 3 milliseconds should capture 3 or 4 cycles of the 1 kilohertz, and then we do a very fine step size, 1 or 2 microseconds. Again, you decide on your result how you're going to actually do that. all this is definitely why you shouldn't be saving between drawing schematics. So now the simulator is highlighted. So we run the simulation, assuming there's no errors on the circuit. And an automatic clock marker is on. And we could open up another window and put the 10 millivolt input. This camera is much smaller than it's much smaller than the output. So the output here is, and you have your calculator open. Open up your calculator. Calculator, the output is 598 minus 598 plus 856.
1454.
And then divide that by 0.02.
You said 0.02?
0.02. What number you get?
72,
72,
700.
72. Okay, that.
72,700.
Now these are in millivolts here. You know, and then the input, not just the input is in 0.02 millivolts. So what gain are you after? Are you getting 72,000 or 72?
72,000. That's what they got. They didn't put it in. How do you convert it?
All right, we'll another calculator. Calculate the gain.
What were the numbers again? 14.
How'd you just add it, right? You just added the two.
Yeah, I think he said that to then divide it after.
And divided by 0.02, right?
Yeah. Because what, 1454 divided by
So
0.
this is VN, which is 20
Yeah, yeah.
millivolts. Keep
Yeah. Should it be a lower number than that?
let's check. We have another calculator number.
About the same thing.
I'm getting 72.7.
Can you repeat the calculations of how we did it again? Because we're dividing it by 0.02, but then we're adding those two together.
We add those two together, 598 times 10 to the minus 3 plus 856 times 10 to the minus 3, and then divide that by 0.02. So that's coming out around 72.7. patterns.
Yeah, we can convert it.
Yeah.
That's what,
We just didn't convert it, Professor.
sorry.
That's what it was.
And the projection from the paper design was 74, minus 74 point. So that's close enough to the paper design, and we also want to check for the inversion here. The upper plot, this is the input, and we notice it's on the our phase with the output. The output has very slight distortion in it, where it's starting to flatten on top and the bottom, so it's almost at kind of its maximum peak output. So you can basically carry these notes for problem 3. I think problem 3 has 3 parts to it. I believe it has 3 parts to it. But this basically gives an introduction at least to the type of circuit that's given here. And 3.2 says, how do you treat the voltage gain down by 5? How do you treat the voltage gain down by 5? How do we treat the voltage gain to down by 5? And we give a hint. Stay away from the collector resistance. Change that collector resistance. It's going to upset the bias in the circuit. So the simplest is probably to play around with the load resistance. And that's because in the gain formula, including for the gain, as the collector parallel to the load, parallel to also. So we probably play around with the load resistance in order to lower the gain. So that's kind of a hint for that. All right, our next session, we're going to actually move over to MOSFET transistor. As I said, for the homework assignment, we definitely want to spend time with these various versions